One of the things that you do in your introductory physics course second semester is to find the electric fields due to charge distributions. Now, one of the charge distributions that you do is the electric field due to a rod. I'm going to do a different problem though. First, normally what you do is you have some rod with a charge Q and length L, and you want to find the electric field on the line perpendicular to that. I'm not going to do that. I'm going to find the electric field along the axis, some distance RO from the center, that location right there, because it's more fun. And then I will do this numerically, and then I will do the electric field, the one that you'll see in the textbooks all the time. And I don't see this one in the textbook too much. I'm kind of surprised because it's super nice. And it's easier to set up. Okay, so the first thing we need to do is to look at the electric field due to a point charge as a reminder. So if I have some point charge right here, Q, at some location RQ, okay, not at the origin, and I have some observation location right here, RO, they're both vectors, then I can find the vector from the charge to the observation location, and I'll call that R. So R is just going to be RO minus RQ. And then I can find the electric field due to that single point charge as 1 over 4 pi epsilon naught, that's just a constant, you may call that K, Q over R squared, R hat. And so you need that R hat in order to get this as a vector. Now, why does it really matter? Because if I want to find the electric field due to this, I can imagine that it's a bunch of point charges, because it is. Okay, so we're going to set this up as an integral and integrate, and then we'll do it numerically. So I want to break this into finite pieces, kind of finite pieces. So let's just say here's my little piece right here. That's a piece, a random piece, and it has a distance x from the origin, and it has a charge. It's not the whole charge. It's just part of the charge. So it's dq. It's a small element of charge. And I want to find the electric field due to this charge at that location. And then I'll just add up the electric field due to all the other charges. So I can use the same idea, right? I know let's first think about this. I'm going to make this a little bit simpler. Because if this makes an electric field over here, dE, and then I move to another piece right here, or right here, or right here, or right here, they're all in the same direction. If they're positive charges, all the electric fields are in the x direction. So I can just solve for the x component of electric field and deal with this as a scalar. So I don't really have to worry about that r hat right now. It makes it a little bit easier. So let's get an expression for dEx due to this charge right here. dEx is 1 over 4 pi epsilon naught. It's a point charge, okay? What's its charge? Q is dq. So it's going to be dq. What's the distance between here and there? Well, if this to here and there is RO, and this is x, this is the leftover distance. So this is going to be RO minus x quantity squared. That's the electric field due to that single piece right there. Now, I want to find the total electric field. I could integrate this side and integrate that side. This is an easy integral. This is not, because my integration variable is dq. I need to switch that to a better integration variable. So let's look at this. If I have the whole rod, then I can say the charge per length Q over L. And then if this is a uniform density, charge density, then the charge per unit length for this has to be the same thing. So it's going to be dq over its length. Its length is going to be dx, right? Because it's a little piece in the x direction. So I can solve this for dq. I get dq equals q over L dx. Now if I put that in over here, I'll get an integration with respect to x, and I can do that. So now if I get the following integral, ex is going to be 1 over 4 pi epsilon naught, integrate from x equals negative L over 2 to x equals L over 2. I'm adding up from here, which is negative L over 2, to here, which is L over 2. And then I have all this. I have dq, which is going to be q over L. I'll put it over here. It's constant. Q over L dx over RO minus x quantity squared. So now I just need to integrate this, and I get my expression. Now, maybe you have a little experience with this, and you can see the trick here. The trick is to say, okay, well, look, I have dx up there. I have kind of an x on the bottom. Let's just say u equals RO minus x. right? So this will be u squared on the bottom. And if that's the case, I need to find out what dx is. So I can take the derivative of this, and I get du equals the derivative of ro, which is just a constant. It doesn't change as I move along here. That doesn't change. So I get negative dx, right? Constant, negative dx. So if I substitute that in, I get the following equation. Let's write it right here. So I get ex equals 1 over 4 pi epsilon naught q over L. I'm just going to leave this as an integral. It's actually integrating over u now, but I don't really care. Negative du over u squared. Okay. So now I can integrate that, right? This is going to be the integral of du over u squared is negative 1 over u. So that negative is going to cancel, and I get 1 over 4 pi epsilon naught q over L. And then I get 1 over u. I'm going to go ahead and put in my value for u, which is ro minus x. So I get 1 over ro minus x, evaluated from x equals negative L over 2 to x equals L over 2. See, if I substitute back into x, I don't have to switch my limits of integration. So now I get ex equals 1 over 4 pi epsilon naught q over L, and then I get this 1 over this evaluated at L over 2, which is going to be r minus L over 2, and then minus 1 over ro plus L over 2. And that's it. That's my expression. Okay. Now, we're going to do this in Python. And I'm going to do it a couple ways. I'm going to do it 2 ways in Python. And in Python, we're doing the same thing. The only difference is we're not going to take a limit as the step size goes to 0 or the piece size goes to 0. We're going to use finite number of pieces. So imagine that I have my rod right here. There's my rod, and I'm going to break this into a bunch of charges. Let's say 5. 5 individual charges, and want to find the electric field right here. Well, for each one of those charges, I just need to find the vector location of, I'm going to use a vector location of the charge. I'll call it RQN. You'll see why. That's the vector location of my observation, RO. And then R is going to be equal to RO minus RQN. And then I can use that to find my electric field. Now, I do need to find the charge of each one of these. The charge is going to be, let's say Qn is going to be the total charge Q divided by the number of pieces N. Now, there is one thing. I could figure out the location of 5 charges, and this would actually give me a pretty good answer. But I want to do it automatically. So what I'm going to do is the following. Let me redraw that stick. And this is a cheat, and we can do a better thing later. But I'm going to start off with the point charge right there at the edge. So let's say R1 is going to be equal to the vector. I'm going to write it as a vector. Negative L over 2. 0, 0. That's the location. Negative L over 2 in the x direction. Now, I need to find the next one I'll move over some step size. So I need to know the step size. So let's say dr equals the total length, L, divided by the number of pieces times 1, 0, 0. Right, so that's the step size. Now, you'll notice that I'm going to end up a little short, and that's okay. I'm really breaking this into pieces, like that. But I'm putting the point charges on the left edge and not in the middle, which is wrong. And I know it's wrong, right? So I know I'm a bad person for doing that, but I'm going to do it anyway. So then I can find the location of any of these charges. I can say Rn, which I called RQN. Rn is going to be equal to R1 plus N times dr, where N is 0, 1, 2, all the way up to N. Okay, so that's what I'm going to do. The first thing I'm going to do is to make these spheres, and then I'm going to calculate this stuff. Now, the other thing, if I'm breaking this into a finite number of points, I'm not going to get a function for the electric field. I'm going to get a numerical value. So I need some values over here. I'm going to say Q is equal to 4 times 10 to the negative 6 coulombs. I'm going to say the length is 0.1 meters. And then we're going to say, let's find, we'll change the observation location. But I'll say it's at 0.2. So I'll say this RO is 0.2 meters. And then 1 over 4 pi epsilon naught is this K, we'll call it K, 9 times 10 to the 9th. Okay, let's jump over to Python and let's make this stuff happen. Okay, computer. Here we are in Python. Okay, so the first thing I'm going to do is I'm going to write down my constants. So K equals 9 times 10 to the 9th. L equals 0.1. Q equals 4 times 10 to the negative 6. And if you've not done Python before, I'm not putting units. They're just numbers. They're just numbers. Okay, so let's go ahead and start with two important vectors. The first one is the starting location, which I'm going to call R1. It's going to be equal to, just like I said, it's going to be the vector negative L over 2, 0, 0. And then I need to get the observation location. I'm just going to call it RO. It's going to be vector, I said 0.2. So it's just going to be 0.200 on the x-axis. And this is the magic part right here, because I can change that location to where. It doesn't, in this method, it doesn't matter what I do. Okay, now let's find, let's say n is equal to 5. I'm just going to use a small number so that we can see if it works. We can always increase that later. With that, I need to calculate my dq. dq is going to be q divided by n. I need my dr, my step size. Dr equals L divided by n times vector 1, 0, 0, right? Because I'm moving in the x direction. Okay, so there's a lot of ways to count, but I'm going to do my favorite way. I'm going to say I'm going to have capital N as the number of pieces, and lowercase n is my count. So I'm going to say n equals 0, and let's just do a count. So I'll say while n is less than n, print n, and then n equals n plus 1, so increase n. I'm going to run it, just so we can see that it does indeed work. So it goes 0, 1, 2, 3, 4. That is 5 numbers, right? Because it started at 0. And that's what I want. Let's save this. Horizontal E rod. I don't know. I'm going to give you the code. Don't worry. I'll give you a link to the code. Okay, so now what I want to do is I'm going to actually draw a sphere at each of those locations. This will help us visualize what's going on. It's not needed for the calculation, but I'm going to do it anyway. So I'm just going to say sphere. No, let's do this. Rn, that's the location of each point, is going to be equal to R1 plus n times dr. Let's just print that. Print Rn to see that it's working. So you see here I go at negative 0.05. That's the far left end. And then it goes up here to 0.03, which is not quite to the right end, but it's going to be close enough. So that looks okay. So I don't need to print this. I'm going to make a sphere. The position is going to be equal to Rn. The radius is going to be equal to L divided by 40. I don't know. Let's pick something. And so it's just going to draw a sphere. It doesn't have a name. It's just drawing a sphere. And it should be 5 spheres. 1, 2, 3, 4, 5. And you'll notice they all shift a little bit to the left. And that's totally fine. Okay, now we can do the fun, awesome stuff. I want to calculate the electric field due to each one of those in my loop. And I'm going to call that dE. So let's just go ahead and do that. So the first thing I'm going to do is calculate the vector R. R is RO minus Rn, right? That's the vector from that current charge that I just made to where I want to calculate the electric field. With that, I can calculate the electric field. It's not the total. It's just a dE. So it's a delta technically, but delta is hard to type in Python, so I do it this way. K times dq, which I have up there, times norm r, which is the unit vector in the direction of r, divided by mag r squared. Now, that doesn't give me the answer because I want to take that and add it up. Instead of saving all of those values, I'm going to just go ahead and add it to the total, but I don't have a total. So I'm going to go up here and say E equals vector 0, 0, 0. So that's the total electric field. It's called E. And I need to start it as something so I can add to it. If it doesn't exist, I can't add to it. So I'm going to start at 0, go through and add up the electric fields. So down here, I'm going to say E equals E plus DE. And then that should be it. Let's print it. Print E equals E newtons per coulomb. And there's my electric field. Okay, that's the electric field due to 1, 2, 3, 4, 5 at the location. I didn't even draw that other vector. You could put you could put a point where the observation location is. You could draw an arrow there, but I don't really care. Okay, we can do that. We can make it pretty later. But I want to compare my two values, right? So I already calculated a theoretical expression for this. So let's print the theoretical expression with the same numbers. So I can call it ET equals, now I'm looking at my equation. Where'd I put it? Oh, there it is. Okay. It's going to be K times Q over L, times 1 divided by RO. Okay, so let's call this a different thing. Let's call this RTO equals mag of RO. Right? That way, I don't have to write magnitude in my thing. It's just really me being lazy, and that's fine. So it's going to be RTO, the T stands for theoretical, minus L over 2. All that minus 1 over RTO plus L over 2. I think that's right. I'm looking at my thing. Okay. And that's print ET newtons per coulomb. So we get something different. Oh, well, I guess it didn't work. Gotcha, it worked. It totally worked, okay? That's just with this breaking this into 5 points. You'll notice it's not even that far off. But if I break it into 5, I can break it into 50. So there's no difference. All I have to do is go over here and change N to 50. Now you see 50 data points, and you get 9.49 times 10 to the 5th and 9.6 times 10 to the 5th. Not that much difference, okay? Now I could even break it into 100 if I want to. And you see it gets even closer. So you can explore the relationship between the two different calculations and the number of data points, and that's just fun to do. And also you could move the observation location away and plot the electric field as a function of distance for both of these functions. Okay, I'm not going to do that just because I don't want this going forever. If you really want me to, I probably would. But I do want to show you one other way to do this, and then I'm going to show you another method. I can actually build my rod and make it a list and then use that list. And that's what I want to do. Okay, so let's do this. Let's say Q's equals a list. I'm not gonna draw them. I'm just gonna put, although I could. Yeah, I'm gonna draw them. I'll draw them anyway. Okay, so I'm gonna do the same part right here. I'm just not gonna calculate the electric field. I am gonna do this part. Don't forget that. Bad stuff happens. Actually, I don't need this R. Put this down here. Let's comment this stuff out, because and if you're looking in Web VPython, I'm using Web VPython. You can comment out a section with the triple quote like that. So when I make my RN, I'm going to add everything to a list, which I have called QS. That's the Q's, right? So I'm going to say QS equals QS plus a list element. And the list element's going to be this. And I'm going to go ahead and put the charge of that list element in here too. So I'm going to say Q equals DQ. You can add a property to that. So now let's just do that, and then let's print. Oh, I can't print. I'm gonna print something. I'll print two things. Watch this. I'll show you that it does. Actually, let me make it first. So it looks the same. I'm gonna change this back to 5. It looks the same. Okay. But what I'm going to do is say print qs0.pos. That's going to be the position of the first element in the queues list. I didn't like that. Oh, indentation problem. Where's my indentation problem? In line 24. What the heck? Line 23. Maybe it's this one. It did it before, though. Okay. QS, let's see. Let me get rid of this line. Maybe it's this line right here. So that ran and printed ET. So where's the indentation problem? Let's put it down here. Print qs0.pos. Okay, I don't know what the problem was. Okay, so that is the vector location. I could also print out the charge of that. So I can reference those values in there. There's the charge. Okay, so now when I want to calculate the electric field, I still need this E equals 0. But I'm going to do another loop. I'm just going to delete that stuff. I'm going to say for QQ in QS. So, and then I'm going to do this. Print qq.pos. So this is a great way to traverse a list. If I have a list of objects, I can refer to each one of them as this thing called QQ. It's going to say QQ is the first one, then QQ is the second one, then QQ, and so forth. I'm going to print out the positions just so you can see how that works. And there's all the positions of my Qs. So I can do my calculation. So now let's do this. Let's calculate R temp. So R is going to be RO minus QQ.pos. So QQ is that element, and POS is the location of that element. So that gives me R. And then I can calculate DE. It's going to be K times QQ.Q, right? QQ.Q is the charge of that particular location, that point. So I've associated that property with that object, times norm R divided by mag R squared. And then I can add that to the total. E equals E plus DE. And then I can print that, and it should give me the same thing as before. Okay, so I have the same value with the 5, so it did work. Okay, so that's kind of cool. So it's a different way. The nice thing about adding these to the list, if I want to do something with that list later, I can just go through the list and do stuff. Okay. Now, here's what I want to show you. So change this to 50. Now, what if I change my observation location right here in the y-axis? Let me set up that problem and then show you the theoretical answer, and then I'll come back and do it. And so you can see what it looks like. So going to here, back to the paper. So this is a harder problem, which makes it better in some ways. But this is the one that you see in the textbooks a lot of times. So it has the same charge rod, but it has it like this. And then here's my observation location. So you're going to do the same thing. You're going to break this into a piece. We'll call that DQ. This is going to be the vector RO. This is the vector RN, right? It's the location of that. And this is going to be the vector R. And you can calculate all this stuff. Now, you can see I can't just smash it into one dimension now. I'm going to get an electric field DE like that. Let's just set this up. So Rn is going to be equal to the vector, some vector 0, y0. It's in the y direction. Ro is going to be something, let's say it's 0.200, just like we had before. It's something in the x direction. So then when I find R, it's going to have an x and a y direction. Now, here's the problem number 1. So I'm going to need to find the magnitude of r. So r is going to be RO minus RN, so it's going to be 0.2 minus y, 0. I'm going to need to find the magnitude and the unit vector. But the trick is, if I look down here, there's another piece that's symmetrical that's going to be up here like that. And so the y components are going to cancel. I'll only get an x component. And then I can integrate along y. And like I said, it's a difficult problem to set up. I have a video going over the solution. I don't want to do it because I want to show you how to do it numerically. I will tell you this. The x component, ex, if it's that way, is going to be equal to 1 over 4 pi. If you set this integral up, epsilon naught, q over RO times the square root of RO squared plus L over 2 quantity squared. So what I want to do is to use the program I just wrote, move my observation location actually into the y direction, because I don't want to move my rod like this. And I'll calculate the electric field due to these points, and then I'll calculate the theoretical and see how they compare. And that's what's really powerful about this numerical method, is that all I need to do is change the observation location and it should still work. Okay, back to the computer. So here we are. Edit. So I'm going to put this at 5, just so I can see it. And then I'm going to put my observation location at point 2 in the y direction, like that. Now if I run it, that's all I have to do. That's all I have to do. And you'll notice that it gives me a smaller x component, and that's because the x components don't cancel because these aren't centered correctly, and the y component is larger. But it's not the same as this other one, so we need to calculate that. So let's call this E parallel, EP for perpendicular. I'm just going to type in the equation, K times Q divided by RO, which is RTO, same distance, RTO. I'm using that same, it doesn't matter, it's in the y direction, times the square root of RTO squared plus L over 2 squared. I think that's it. So let's print that. I'll call it EP and newtons per coulomb. And let's run it. Okay, so here's my electric field in the, due to the numerical values, 8.7 times 10 to the fifth. And here you see I get very close to the same thing. I have no y component. Let's increase the number of points to 50. And that x component should be going away. Yeah, so now it's a lot smaller x component here. Still, they're not centered perfectly. We could fix that. I'm not going to fix that. You could fix that on your own. It's pretty easy to fix, to tell you the truth. But you could do that, and it works pretty well, right? And the other thing is, I could put my observation location anywhere. If you put your observation location right here, that's a pretty hard integral to evaluate. But numerically, it's the same thing. So that's what's really great about these numerical calculations. And like I said, the code for this will be down below. Hopefully that helps, and I'll talk to you later.